Hi guys. Now in this video we will discuss about the Newton's laws of motions and their validity. So starting from the first law of motion. So it is law of inertia, and let me first of all describe the inertia. So inertia is a property of a body. It is a inherent property. Inherent means it is with that body from its birth. So inertia is a property of any object which has some mass, and by the virtue of this property, that body tries to be in rest if it is already in the state of rest. If that body is in the state of motion, then it tries to be in the state of motion. And if that body is moving in a particular direction, then it will try always to move in that same particular direction without changing the direction. This property of not changing the state of rest or motion is known as inertia. So now what does the first law of motion says? It says that each body continues to be in the state of rest or in the state of uniform motion in a straight line until and unless it is being compelled by some external force to change its state. It means कि until and unless some body is being acted upon by some force which is applied to change its state of rest or motion, then that body will not change its state of motion or state of rest until and unless some force which is applied on that body for that changing purpose. So Newton's first law also defines the inertia, and hence it is also called as law of inertia. And it also concludes that Newton's laws are only valid in inertial frame of references, which means the frame of reference, the observers which have zero acceleration are known as inertial frame of reference, and Newton's laws are always defined only in inertial frame of references. So we can say that if we need to apply the Newton's laws of motion from non-inertial frame of reference, then there is another method, or there is another concept of pseudo force which we will introduce in later videos, which is used to apply the Newton's laws of motion from non-inertial frame of references. And non-inertial frame of references are those observers of motion which are accelerated, and inertial frame of references are those observers which are non-accelerated observers. Okay, so in 1803, Newton wrote in Latin that every body preserves its state of rest or of uniform motion in right line unless it is compelled to change that state by forces impressed on it, which means each and every body will keep on moving or it will stay in the state of rest until and unless some force is applied on that body to change its state of rest or its state of uniform motion. So it concludes that if we are not applying any force to change the state of rest or motion, the body will not change the state of rest or motion. If it is in the state of rest, it will stay in that state, it will not move. And if it is moving in a particular direction with some constant velocity, then if there is no force applied on it, then it will keep on moving in the same direction with that same particular velocity. Now the Newton's second law of motion states that the rate of change of momentum of a body is proportional to the applied force, and it takes place in the direction of the force which is applied on it. Which means the when we apply some force on a body, then that force changes the momentum of that body, and this change in momentum also occurs in the direction of force. Now, greater the force you apply, greater will be the rate of change of momentum. So, rate of change of momentum is directly proportional to the applied force. And in 1803, the translation of Newton's Latin statement was the alteration of motion is ever proportional to the motive force impressed, which means that motion, if the motion will change, then its change will be proportional to the force that is applied to change the motion, and this and is made in the direction of right line in which that force is impressed, and this alteration of motion occurs in the direction in which that force is impressed. So that force F is proportional to dp by dt, and when we remove the proportionality sign and some constant appears, and the value of that constant experimentally is 1, and this dp by dt, we can say that p momentum p is equal to mv, mass into velocity. Now dp by dp by dt is equal to d by dt into mv, and taking out the constant quantity mass, then it will be dv by dt, and this dv by dt is acceleration. So we can conclude that according to Newton's second law, F is equal to ma, where m is the mass of the body on which force is applied, and F is that force which is applied on that body, and A is its acceleration. Now, if in case two particles which are having linear momentum p1 and p2 are moving towards each other under the mutual forces, then according to Newton's second law, applied on the system of those two bodies. Let's suppose there is a system of two bodies, like this is 1 and this is 2, and they are moving towards each other. So it has a momentum of p1 and it has a momentum of p2. So as we know that the net force on this system is 0. Okay, so we can say that sum of the momentums, the rate of change of the sum of the momentums will be 0, because the net force acting on the system is 0, and which means that dp1 upon dt plus dp2 upon dt will be 0. Now dp1 by dt is the force acting on this particle 1, F1, and dp2 by dt is the force acting on this particle F2. So F1 plus F2 will be equal to 0, and F1 will be equal to minus F2. Now these forces are acting internally on the particles, and these are the internal forces of the system, and the net external force on the system is 0. So it also leads to the conclusion that if a system has no external force acting on it, and it has some components which are moving under the mutual forces, then the mutual forces are always equal and opposite to the to each other, which means that the force acting on one F1 and the force acting on 2 F2 will be always equal in magnitude, and they will be opposite in direction. And this is the Newton's third law. Now we are discussing some important points about second law, And the first point is the fact that the second law is obviously consistent with the first law, as f is equal to 0 and a is equal to 0. So obviously we have already discussed that if no force is acting on a body or a system, then its momentum will not change. And here momentum is the state of motion. If the body is in a state of rest, then its momentum will be 0. And if a body is moving uniformly in a straight line, then its momentum will be constant. So momentum will not change if that body is not acted upon by some force. Now, if we apply this second law in vector form, then we know that there are three fundamental directions of motion: x, y, and z. And the force which is acted on the body in the direction of x-axis, then it will only change the momentum of x-axis. And similarly, the force acting along y will change the momentum along y, and the force acting along z will change the momentum of z-axis. Okay, now this means that if a force is not parallel to the velocity of body, but it is making some angle with it, then it changes only the component of velocity that is along the direction of force, and component of the velocity that is normal to the force will remain unchanged. It means that if a body has a velocity in this direction and the force is acting in this direction, so the velocity component which is parallel to this force, v parallel, and the one component is perpendicular to the force. So as we know that force will change only that component which is in the direction of force, so it will be changing, v parallel will be changing and v perpendicular will remain constant, as there is no force acting in the direction of v perpendicular. Now this second law of motion which is given above is strictly applicable to a single point mass, which means when we are applying this law of motion, then this F force stands for the next net external force which is acting on that particle, and A stands for the acceleration of that particle. Now any internal force of the system is not included in this force F. So it is valid for a system keeping in mind that that force F, which when we write F is equal to ma, then F is the net force acting on that system, and A is the acceleration of that complete system, or we can say that the A is the acceleration of the center of mass of that system, and center of mass is a single mass representative of a system. Now the second law of motion is also a local relation. It means that when we write F is equal to ma, then the instant at which that F is applicable on the body, A is the acceleration of that same instant. The acceleration has no relation with the history of the motion, and the instant we are applying any force on the body, at the same instant that acceleration is valid. So F is equal to ma has the same instant relationship. Now Newton's third law of motion, we always say that every action has equal and opposite reactions, and sometime I ask some students that can you explain practically the Newton's third law of motion. Then they give me the example that there were two friends, Mahesh and Suresh, and Mahesh slapped the Suresh, and Suresh started to cry. So Mahesh does some action on Suresh, and Suresh gave out their reaction. So this is emotions, and emotions are not the part of Newton's third law. When we say that to every action there is equal and opposite reaction, and these action reactions are forces which are acted upon by the bodies on each other. So, from the Latin to English transformation, Newton wrote that to every action there is always opposed and equal opposite reaction, and the mutual actions of the bodies upon each other are always equal and directed to the contrary parts, which means when we push a wall, we are doing some action, which means we are applying some force on the wall. So action is being done by us on the wall, and the same force, the equal force wall will apply on us. So we have to note the fact that the intensity of force or the intensity of punch, if I punch the wall, the intensity of my punch will give out the same equal reaction on my hand, and the probability that my hand will break will depend on the intensity of punch with which I will hit the wall. So the intense punch will break my own hand, due to the fact that the more I apply the force on wall will give me the equal greater reaction on my hand. Now, the another thing which is to note is that the fact that the action is occurring on the wall and a reaction is occurring on my hand. Action is being done by my hand and reaction is being given by the wall. So you can see that the action reactions are forces. They are equal in magnitude and they are opposite in directions. Opposite in the sense that when I am applying the force on the wall, then it is in some particular direction towards the wall, and at the same instant wall is giving me the reaction which is exactly in the opposite direction to the action which I have produced. So so important points are the terms action and reactions in the third law means nothing, means forces, and it is a simple and clear way of stating the Newton's third law that force always occurs in pairs. Force on a body A by B is equal and opposite to the force on body B by A. So we have discussed with that example already. The term action reaction in the third law may give wrong impression that action comes before reaction. Action is cause and reaction is effect. Obviously, when we hit the wall, then only reaction is produced. So cause of reaction is action, and effect of action is reaction. So there is no such cause-effect relation implied in third law, and the force on A by B and the force on B by A act at the same instant. Any one of them may be called as action and other as reaction. Obviously, we can say that when the instant when we are hitting the wall, at the same instant a wall is hitting us back. So if from our perspective we are saying that we have done some action on the wall, then from the wall's perspective we can say that wall has done some action on us and we have given the same reaction to the wall. Now, action and reaction forces act on different bodies, not on the same body. Obviously, when we hit a wall, then action is being done on the wall and reaction is being given to the body, to us who is hitting the wall. Thus, if we are considering the motion of any one body, A or B, then only one of the two forces is relevant. Then it is an error to add up the two forces and claim that it is a net force is zero. Obviously, most of the students do commit this error, that they say that when we hit a wall or when we do some action on somebody, then we say that action and reactions are equal and opposite, so they should cancel out, and therefore there should be no effect of that action on any of the body. But it is wrong, because we cannot cancel out the forces acting on two different bodies. We can sum up the vector sum of the forces acting on a single body only. And and in the action reaction pair, action is acting on some other body and reaction is acting on some other body, so we cannot sum up these forces, claiming them on a single body. This is a wrong approach. Now, if we are considering a system of two bodies as a complete system, then force of A due to B and force of B due to A are the internal forces of the system. System consists of the two bodies A and B. They add up to give a null force. So when there is a system, let's suppose an example that there is a system and there is a body A and there is a body B. So force on A due to B, which we can say FAB, and force on B due to A, which we can say FBA. Now these forces are obviously acting on different bodies A and B, and we cannot say that the net force on A is 0 and net force on B is 0, but we can say that net force on this system is 0, because these two forces are a part of a single system, and when they will sum up in the system, then they will cancel out with each other because they are in opposite directions and they are equal in magnitude. So that it is important to note that the fact that second law is applicable to a body or a system also, and the sum of the internal forces acting in a system is always 0 and they cancels in pairs. So these was the explanations of Newton's laws of motion, and after this video we'll come up with the numerical portion of the NLM. Thank you.